So let's go back to this problem that I accidentally skipped over, so sorry about that. Kind of doing these examples out of order. So this example is very similar to the example here on slide 24. So we need to know the magnetic field strength some distance from the wire, but we have to know its direction too, and the reason we have to know its direction is because we have a charged particle. There's an electron that is moving near the wire, and so this charge is in the presence of a magnetic field that is being generated by this wire. So I'm going to draw, or I'm going to show you a diagram of what's happening. So we're actually going to use two right-hand rules. We're going to determine the direction of the magnetic field, some location near the wire, and then we're going to use our original right-hand rule, F equals QVB, to find the direction of the magnetic force on the electron. And of course we're going to calculate the magnitudes of the magnetic field and the magnetic force on the electron. So the wire is carrying a 10 amp current, and we know the location in question is 1 centimeter above the wire. And so we also know the speed of the electron, which is 1 times 10 to the 7 meters per second. So my drawing for this picture looks like this. So it says the current is going from left to right in the wire. So I draw the wire like this. The current's going left to right, and the problem says that there's an electron, what was the distance? 1 centimeter above the wire. So here's the electron, negatively charged. So when we do our right-hand rule to find the force on this charged particle, we're going to have to flip it because it's negatively charged. So my first right-hand rule is grabbing the wire with my right hand with my thumb in the direction of the current. So I'm grabbing the wire. So I'm going to start with my hand, my palm facing up. The palm of my right hand is facing up right now. My thumb is pointing to the right. So I'm going to grab the wire kind of from underneath it. I'm grabbing the wire. And so as I grab the wire, I curl my fingers. My fingers are going into the page below the wire. And then as I grab the wire, my fingers are pointing back towards me above the wire. Right, so you can kind of picture as you're grabbing the wire, you grab it from underneath, your fingers go into the page below the wire, and then they curl up behind it and then around it, and your fingers are pointing towards you when you grab the wire. So that's the direction of the magnetic field above the wire. It's out of the page. Okay, so it's towards us. Now I'm going to use the first right-hand rule for QVB to find the direction of the magnetic force on this particle due to the magnetic field. So my second right-hand rule is fingers in the direction of V, curl them in the direction of B. Now this is a little bit awkward, so I still have to use my right hand. I point the fingers of my right hand in the direction of V. My palm is kind of facing me. Alright? So my fingers are in the positive X direction. They're pointing to the right. My palm is facing me. I want to curl my fingers in the direction of the B field. So I'm actually curling them towards me. And my thumb is pointing down right now. Okay? So V cross B gives me a direction that's the negative Y direction. Okay, negative Y direction. So that's the direction your thumb should be pointing in right now. That would be for a positive charge. So remember, if we're dealing with a negative charge, we have to flip the direction. So you flip your thumb, give it a thumbs up, and the force on this charge is actually going to be in the positive y direction. Okay, so we use one right hand rule to determine the direction of the magnetic field above the wire, and then we used our right hand rule for QVB to find the direction of the force on this negatively charged particle. So now that I've got my directions taken care of, I'm going to use the values. I'm going to use the values that were given to calculate the magnitudes. I've got a 10 amp current. The electron is 10 centimeters above the wire, and the speed of the electron is 1 times 10 to the 7 meters per second. So the first thing we're going to do is we're going to calculate the magnitude of the magnetic field using mu naught I over 2 pi r. So I've got a 10 amp current. I'm 10 centimeters away from the wire. Using this expression, I calculate the magnetic field, which is 2 times 10 to the negative 4 Tesla. Final step, I did step 3 first. I did the directions first. Final step is finding the magnitude of the force. We see that the velocity vector was perpendicular to the magnetic field vector in our diagram. So it's an electron, 1.6 times 10 to the negative 19 coulombs. Yes, that's negative, but I accounted for that when I flipped the direction of my thumb for the right hand rule. So I'm just going to use the magnitude of the charge here because I already know the direction. Singly charged, it's an electron. It's got a velocity of 1 times 10 to the 7 meters per second, and I calculated the magnetic field strength from the first part, which is 2 times 10 to the negative 4 Tesla. When I calculate this, I get a force of 3.2 times 10 to the negative 16 newtons. So again, we're dealing with very small forces, but the particles have a very, very low mass, so little extra practice, take the net force, divide it by the mass of the electron, and you'd get the acceleration, which should actually be pretty high, because you'd have 10 to the negative 16 divided by 10 to the negative 31, so you'd still have a very high acceleration. Okay, so we'll get back on track with these with this magnetic field superposition example. So I've got 2 more examples, and that should wrap up chapter 19. I've got 2 wires. Both have currents of 10 amps going through them. This wire, it's at 1, 1, has a current of 10 amps out of the page, so it's towards us. The current in this wire that's at 1, -1 is also 10 amps, but it's into the page. So we want the magnitude and the direction of the net magnetic field due to both wires at all 3 of these points, A, B, and C. So A is the origin, B is 1, 0, and C is 2, 0. So let's use the right hand rule for both of these wires and get a sense of the direction of the magnetic fields at location A. So I'm using the right hand rule for the top wire, 10 amp wire. So I have to grab that wire, but my thumb has to be pointing in the direction of the current. So my thumb is pointing towards me right now, and I'm curling my fingers around the wire to grab it. So my fingers should be going in the clockwise direction. Clockwise direction, clockwise direction. So if you have a printer or maybe you have a tablet or something you can draw on, try and draw a circle. Okay, try and draw a circle around the current carrying wire that passes through point A. Okay, if you draw this circle that goes through point A, you'll see that the magnetic field is going to be tangent to the circle. The circle comes around. The magnetic field due to that top wire is going to go like this. Right? Magnetic field is going to be going in the positive X and the negative Y direction. Okay? We draw that circle around the current carrying wire. It comes around like this. The magnetic field is tangential to the circle, and so it's going to be like this. And I'll show you in my solutions a diagram. Let's do the same thing for this wire. I'm going to draw another circle around that, but this time my thumb is pointing into the page. So the magnetic field around this wire is actually clockwise. So it's clockwise around this wire. So if I draw a similar circle going around, and I hit point A, my magnetic field is going to be tangent to that circle. So it's in the first quadrant. It's positive X, positive Y. Okay. So this is my diagram right here. Alright, this is my diagram for point A. Alright. This is the magnetic field due to the top wire. This is the magnetic field due to the bottom wire. And we see that the way I got those angles is that right here is a right triangle. Okay, but it's a 45, 45, 90. You see I'm at 1, 1. Down here I'm at 1, -1. Right, so I'm actually making squares and nice right isosceles triangles. Okay, so they're giving me nice angles of 45 degrees below the positive x-axis and 45 degrees above the positive x-axis. So these are very, very nice angles right here. Okay, so for part A, my axis, my scale is actually centimeters, so I have to watch out for that, right? My scale is centimeters. So I'm using mu naught I over 2 pi r to calculate their magnitudes. So I know the currents are 10 amps. I actually have to find this distance r. Right? Now this is the hypotenuse of this right triangle. 1 centimeter, 1 centimeter. This is 1 times √2 centimeters. Okay. Now I was a geometry teacher back in the day, so I got my special right triangles still committed to memory. If you don't, you can still use the Pythagorean theorem. So this is 1 squared plus 1 squared, all right, is equal to the hypotenuse squared. So you can still calculate that, and you'd still get the square root of 2 as your hypotenuse. So this distance is √2. You get like 1.7 something, and this distance is also √2. So that's what I'm going to use for my r when I'm calculating the magnitude of the magnetic field. All right. So 1.414. Sorry, 1.7 is like √3. My mistake. So I guess I wasn't that great of a geometry teacher after all. So B1 is acting at 45 degrees. B2 is also acting at 45 degrees. So they both have an x component and they have a y component. All right. So the magnitude of B1 is mu naught times the current divided by 2 pi times r. So I get √2 times 10 to the -4 Tesla, or 1.414 times 10 to the -4 Tesla. Now both of these wires are carrying the same current, all right, and they're the same distance from point A. So the magnitude of B1 is actually the same magnitude as B2. So the magnitudes are the same. So the magnetic field strength due to both of these wires is the same at point A. But they're pointing in different directions, so I have to resolve them into their x and their y components. So B1 in the x direction is the magnitude times the cosine of 45. Same thing with B2. It's the magnitude of B2 times the cosine of 45. But we know B1 and B2 are the same. All right. So B1 times the cosine of 45 in the x direction, B2 times the cosine of 45 in the x direction. They're both positive. You see from the diagram, both of their x components are positive. So we're going to add these two terms together, B1 cosine 45 plus B2 cosine 45, to get the net magnetic field in the x direction. And so I'm using cosine of 45 as √2 over 2. And the reason I'm doing that is because I'm using my radicals instead of the decimals. You can use the decimals, that's fine. Just do the calculation. But I noticed that √2 times √2 is 2, and 2 divided by 2 is 1. And so it made my math a little bit easier for me to do by hand here. So this is b1 in the x direction, b1 times the cosine of 45. This is b2 in the x direction. I'm adding them, they're both in the positive x direction. So this is b2 times the cosine of 45. When I add them together, I get 2 times 10 to the negative 4 Tesla in the x direction. Because their individual x components are 1 times 10 to the negative 4 Tesla. When I add them up, I just get 2 times 10 to the negative 4 Tesla in the x direction. Now what happens in the y direction, b2 in the y direction is b2 times the sine of 45. That's the vertical component. b1 in the y direction is b1 times the sine of 45. The cosine of 45 is equal to the sine of 45. It's root 2 over 2. So b2's y component is positive, b1's y component is negative. So these are actually going to cancel each other out. When I add these two y components together, I'm going to get 0. So the b fields in the y direction are actually canceling out at point A. So the net magnetic field is just in the x direction at point A. The y components are canceling out, and the x components are adding because they're both in the positive x direction. So let's talk about point B. Point B is very nice. So we keep going along. There's a different circle, right? Our R is different. You see that we're not using that root 2 anymore. We're using 1. Okay, so the distance between each wire and point B is just 1 centimeter. Okay, so that's what we're going to use for our R values when we're calculating the magnitude of the magnetic field. So we're drawing a different circle. Okay, I'm still using the right hand rule, right? It's still counterclockwise around this wire, and it's still clockwise around this wire. Okay, so we're drawing our circle, comes around, going through part B, and then it comes back around. The B field is tangent to that circle, and so the B field here, due to this wire, is just the positive x direction. Thank goodness I don't have to resolve it into x and y components. It's just acting in the positive x direction, so good for us. Same thing here. I'm going to draw my circle. Come around. It's clockwise because this current is going into the page. Same circle, okay, but it's clockwise. When I get here, the magnetic field due to this wire is also in the positive x direction. Awesome. So all I got to do is calculate the magnetic field due to this wire and this wire. They're both acting in the positive x direction, so I don't have to resolve vectors. All I have to do is add them. So B1 and B2 are both in the x direction, so all I got to do is find their magnitudes, add them together, and that's the net magnetic field. So the difference here is that I'm using that different R value. So it's not root 2 centimeters from point B, it's just 1 centimeter from point B. Okay, so calculating B1, the magnetic field due to the top wire, mu naught times I, current is still 10 amps, over 2 pi R, I get 2 times 10 to the negative 4 Tesla in the positive x direction. B2 is the same distance from location B, and it's the same current, so B2 is going to be equal to B1. I'm going to do the same calculation. B2 is also 2 times 10 to the negative 4 Tesla, so I add B1 and B2, which is this quantity times 2, so it's just 4 times 10 to the negative 4 Tesla. Right? Easy day, we don't have any y components, all we have to do is add B1 and B2. They're both acting in the positive x direction. So that's the net magnetic field at point B. Point C we'll see is very similar to point A. The issue is our circle comes around. We're talking about this top wire right here. Circle comes around, it's counterclockwise. Keep going, And when we pass through C, the magnetic field due to this wire is now in the positive X and positive Y direction like this, right? So it's a positive X, positive Y vector. It's going like that. This wire, we're drawing our same circle, coming around, coming around, coming around. We go through C, right? Coming around, we go through C, and then we're actually in the negative X and the positive Y direction, right? So the magnetic field due to the 10 amp current is going like this, right? Tangent to that circle. And then this, oh, I'm sorry, excuse me. So this is counterclockwise, right? So I'm good for this magnetic field. It goes like this, right? So I actually got that backwards. Do the right hand rule again. This current is going into the wire. So my circle is going like this, right? My circle is going clockwise, clockwise, clockwise. When I hit C, it's going in this direction right here. Okay. So it looks very, very similar to A, right? We've got a vector, we've got a magnetic field due to this wire in the positive X, positive Y. Now we've got a magnetic field due to this wire in the positive X and the negative Y direction. Okay. Again, sorry about that mix-up, but here is the diagram. Again, it looks very, very similar to part A, right? The difference is B1 and B2, the magnetic fields due to the wires, their directions are flipped. So now I have B1 and B2. We see our algebra is the same. We're still dealing with two magnetic field vectors, the same distance from point C, which is √2 centimeters. We're going to resolve them into their X and Y components again. Okay. Their Y components, we see that they're going to cancel, again, just like they did with part A. So I don't have to worry about any magnetic field in the Y direction. All I have to do is find their X components. So B1 times the cosine of 45 plus B2 times the cosine of 45. So it's √2 times 10 to the negative 4 Tesla times the cosine of 45 plus √2 times 10 to the negative 4 Tesla again times the cosine of 45. I add them up. √2 times √2 is 2. Divided by 2, that cancels, so I get 10 to the negative 4 Tesla plus 10 to the negative 4 Tesla, which is 2 times 10 to the negative 4 Tesla in the X direction. So our answer to part C is the same as the answer to part A. The difference is the direction of the magnetic field vectors are switched, right? So now B1 is acting in this direction, B2 is acting in this direction. All right, last example. We have one more example. It's very similar. The issue here now is the currents are different. So I've got a 5 amp current here, a 3 amp current here, and they're both coming out of the page. So we'll find our directions using our right-hand rules. We'll calculate using the currents and the distance between the wire and that point. So we can find the magnitude and the direction due to the two magnetic fields from these two wires. Let's start with this one. This one looks pretty easy, right? Straight line distance 20 centimeters. Current is 5 amps. So I'm going to start with pointing my thumb towards me because the current is coming out of the page. Curl my fingers around the current, or around the current carrying wire. So my fingers are curling around like this. Curling around like this. Draw your circle till it passes through point P. Boom. Passes through point P. So a line tangent to that circle is going in the negative X direction. So that's good. Again, I don't have to worry about a Y component here. Alright? So the magnetic field due to this wire, the 5 amp wire, is in the negative X direction. Here, I got my circle, still going counterclockwise, same right hand rule, thumb pointed towards me, my fingers are curling counterclockwise around the wire, and my circle passes through point P like this. So that means the magnetic field due to the 3 amp wire is actually in the negative X direction and the positive Y direction. Okay, and again we've got a nice 45, 45, 90 triangle, all right? So this line, this R vector, right, it goes up like this, and my magnetic field vector is going to be perpendicular to that, right? So it's going like that, okay? So this angle right here, okay, makes a 45-degree angle with a horizontal line here, okay? My magnetic field vector is also going to make a 45-degree angle with the horizontal line passing through P. So here's my diagram of the two magnetic field vectors. B5 is acting strictly in the negative x direction. B3 is acting at 45 degrees above the negative x-axis in the negative x and the positive y direction. So we'll calculate the magnitude of B5 first, because it only has an x component. So mu naught, 5 amps, over 2 pi times 20 centimeters. So 20 centimeters is the distance between the 5 amp current carrying wire and point P. So I get a magnitude of 5 times 10 to the negative 6 Tesla for B5. The magnitude of B3, mu naught, I've got a different current now, divided by 2 pi times that distance. Again, we're dealing with another nice 45, 45, 90. So 20 centimeters, do the Pythagorean theorem, or it's a right isosceles, so it's x root 2. So it's 20 times root 2 centimeters is the distance between the 3 amp current carrying wire and point P. So I'm using 20 root 2 centimeters right here. And I get a magnitude of 2.12 times 10 to the negative 6 Tesla. B net in the x direction is B3 cosine 45, so it's the x component of my B3 vector. That's negative, it's acting in the negative x direction, minus B5. B5 is strictly acting in the x direction, so it doesn't have any y component. So negative B3 cosine of 45 minus B5 gives me negative 6.5 times 10 to the negative 6 Tesla. So B3 is this number, multiply that by the cosine of 45, plus B5 gets me that number, all right? And it's in the negative x direction. B net in the y direction is just the y component of B3. B5 isn't acting in the x direction. So B3 times the sine of 45 is 1.5 times 10 to the negative 6 Tesla. So I have a net magnetic field in the x direction here and a net magnetic field in the y direction here. I'm looking for the magnitude. We use our Pythagorean theorem like we did for our vectors in the past. Bx squared plus by squared. The square root of all that, I get 6.7 times 10 to the negative 6 Tesla. So that's the magnitude of the net magnetic field. I need the angle, all right? I need the direction that this net magnetic field is pointing in. So I take the inverse tangent of the y component over the x component. So I have a positive y component, a negative x component. So my angle is going to be above the negative x axis. Negative x, positive y. I'm pointing in the second quadrant. So this angle that I calculate is above the negative x-axis, and I get 13 degrees. So I'm 13 degrees above the negative x-axis with this magnitude, combination of B3 and B5. Okay, so that wraps up chapter 19. I'll get started on chapter 20. Any issues with magnetism up to this point, please reach out to me. We can email, I can Zoom anytime, at least within reasonable hours. I got an old person's bedtime, so but just get in touch with me. You have any questions, let me know. We can talk over email or Zoom, whatever you want to do. All right, thanks. See ya.